No. So, students, let us start with non-rotating black holes. That means the solution of vacuum solution that we have obtained. That is the so-called Schwarzschild metric, and it is given by this metric line element, and which you are very familiar with. This is the uh, temporal part, and this are the spatial part. This is the radial, and this is the angular part. What is the problem with the coordinate system is that a particular coordinate system can cover only a portion of the manifold. Okay, it cannot cover the whole manifold. Some points are left beyond. So let us see what is this Schwarzschild coordinates covers. The Schwarzschild coordinate ranges between, let us, the coordinate are t, r, theta and phi, and let us check the range. T runs from minus infinity to plus infinity, r runs from 0 to infinity, theta from 0 to pi, and phi from 0 to 2 pi. Okay, this is the whole range of the Schwarzschild coordinates. This is the so-called Schwarzschild coordinate. This can be corrected by uh, see, there are problems with this coordinate. What are the problems with a coordinate in Schwarzschild coordinate is that there are some degeneracy. Okay, what are the degenerate points in Schwarzschild coordinate? The degenerate points in Schwarzschild metric are this r equal to 2m and r equal to 0. Uh, so 2m means twice gm. Let us call it as twice m from now on. Okay, and this r equal to twice 2m is known as Schwarzschild radius, which is the point of interest to us. Okay, we will come to this in a few seconds. So if I put this here, it r equal to 2m in the metric. Okay, so means 2gm means 2m. So it is, if I put this r equal to r, this will be 0. However, the problem with here is this will blow up. There is a degenerate point here. Okay, so this, therefore the Schwarzschild coordinate cannot uh, miss out on this point. So what can be done with this type of coordinate system is that we can choose some another new coordinate system where these things can be bypassed. So some degeneracy can be removed by the introduction of a new coordinate system, and such points are known as coordinate singularity. And can let us check whether this r equal to 2m is a coordinate singularity or not. So this r equal to 2m is a hypersurface. Okay, this is a hypersurface which is is the surface of some two sphere. Okay, and if I calculate the quantity, this Einstein tensor, a compressed form of Einstein tensor, we see that this is 48 m square r to the minus 6. Okay, however, this quantity is a relevant quantity. So this quantity usually tells us whether a coordinate is a means coordinate singularity or not. So you see that r equal to 2m, this things doesn't blow up, although the metric blows up, but the Einstein tensor doesn't blows up. Okay, so we can now say that this r equal to m is a coordinate singularity which can be bypassed, or which can be managed with some change of coordinate system. However, you look into the other one, r equal to 0. Okay, if I put r equal to 0 in this equation, this thing blows up. So this is an intrinsic singularity. It is not a coordinate singularity. Okay, so r equal to 2m is also known as the null hypersurface, because if I put r equal to 2m here, the square becomes 0 for a particular uh, hypersurface of particular theta and phi. Okay, now, we also will encounter something known as null geodesic from now on. What are the null geodesic? Null geodesic are nothing but word lines of massless particle for Schwarzschild coordinate. Okay, so it is the path in which this light or massless particle travels. So if I uh, solve that in Schwarzschild geometry, t dot means with respect to proper time. Okay, or any good affine parameter. For photon, for massive particle, it is proper time. For photon, it is some very good affine parameter. Okay, if I take that, if I divide that both side by that parameter, we see that this is the equation that gives us the word line of a massless particle. Okay, also the T equation of motion which you can find from this, knowing this Lagrangian of this Schwarzschild metric, and it gives 1 minus 2m by r t dot equal to constant. Okay, and it is and if the null geodesic is a radial null geodesic, that is radially some for some fixed theta equal to constant and phi equal to constant. So we have this three equations. Now we can solve this three equation and find that r dot square is given by k square, some constant, this constant. Okay, so r dot this is not, there will not be any square here, r dot equal to plus minus k. So we can write that r lambda, in this is the affine parameter which is defining this photon or the light ray, is given by plus minus of k lambda. If I take the positive case, for the positive case, if I take dt by dr, I can write it in terms of t dot by r dot, which becomes plus minus 1 minus 2m by r to the power minus 1. Okay, so this equation can be solved to get tr as a function of r plus twice m log of r minus 2m minus 1 plus some constant. Okay, where dt by dr, this measures the slope of the rightness in the tr plane. Okay, and you see that the slope is some weird quantity. Okay, and it changes with r. But however, if you can observe cleanly, at r tends to infinity, this slope goes to plus minus 1. However, at r tends to twice m, this slope goes to plus minus infinity. So this is the problematic point, r equal to twice m. So this is the flat space at very far distance. This is flat space which we know asymptotically flat. Schwarzschild metric is also, this gives a good result. However, this is the problem with is this point. So we have to do something about it. So before doing that, okay, so what does this tells us? The light rays which approach r equal to 2m never seems to get there, or at least in the coordinate system, in this Schwarzschild coordinate system, it seems that it never reaches there. Okay, the light ray will approach. However, this is an illusion. How we can see there? We will see later whether this is an illusion or this is an illusion. So what we observe keenly, that the observer at infinity never able to tell that. That means this is an illusion. He always finds that the light rays are not going, approaching, but it's not. It is taking more and more time interval. For as it approaches r equal to twice m, the time interval gets stretches. As you know that the gravitational redshift is there. As I am measuring the time, I am feeling that the time is becoming very large. The calculation that I showed last week. Okay, so the light never reaches there. However, appropriate question is, do the astronaut falling into the black hole really reach r equal to 2m in finite amount of their proper time, This is the main important, whether they reach or not. Okay, that's which we should see about, and we can be pretty sure that they reach r equal to 2m in their proper time within a 5 time. But means black hole are very gravitational effect are very high, so tidal effects are such that they will tear they will torn this astronaut apart and in pieces, and atoms will be taken into pieces, and everything will happen there. However, if I say I can construct something which doesn't overcome all this, then in their proper time they can reach r equal to twice m. Okay, so this is the problematic point which I have always telling about, r equal to twice m. What we can do about it? So this is the first hint, whether we can do something about it or not. So let us choose a coordinate r star. Let us define it by r star, which is given by r plus twice m ln r by twice m minus 1. This is known as the tortoise coordinate. What does this does? If I then take t equal to r plus some constant, then the Schwarzschild metric in this coordinate you can calculate first. This is a homework. Calculate this. That this Schwarzschild metric becomes 1 minus 2m by r minus dt square plus dr square plus this angular part. So metric coefficient does not become infinity r equal to twice m. Okay, this is the important point. The metric coefficient doesn't become infinity r equal to twice m. So we can if I choose t equal to r star plus constant, we will be having outgoing null geodesic. Okay, and if I choose t equal to r star plus constant, we will be getting it, which is solved by this negative of this r equal to plus minus k lambda. The negative, if I take the negative solution, I will get t equal to minus r plus constant, which is the incoming null geodesic. So we can do something about the coordinate system. But before we go to the coordinate system, let us see how the space-time diagram looks like in this uh, social geometry. Okay, now this is the, let us say that this is the t-axis and this is the r-axis. So let us now draw the uh, 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 null geodesic. Okay, so this is the outgoing null geodesics. Okay, if I draw like this, okay, this are the outgoing, all of the outgoing null geodesic, and whereas this dashed line are the incoming null geodesic. Okay, these are all these things. Okay, so you see, first we see, what we see is the light cones. As we see that as we go towards r equal to twice m, the light cones get squeezed. Okay, okay, so this is one of the important, and the light cones beyond r equal to twice m are inverted like this, and they squeezed as we go towards r equal to 0. This is okay. Okay, however, this things is an important observation. Okay, and another thing is that it looks like there is, this is going like this, however, and then it is coming like this. So is there anything here? Is there, we are missing some information here? We can be very naive about it, and still we should make the claim that if there is anything, that this is, there is something which joins like this. Okay, which joins like this, which joins like this. If this joins like this, then this will be interesting, right? So is there anything, can we be sure? Is there anything that, you know, this looks something like a suspicious? Okay, so this, and this is because, as I have told you, the chart doesn't encompass the whole space-time. Okay, it looks like I have this space-time with theta phi and r equal to from 0 to infinity. Okay, however, this t, there is something like small like there, and t has been blown up to plus infinity to minus infinity. What it has done, that it has obscured our view of what is the actual, is there any actual thing which is happening there. Okay, so this thing we should look carefully. So can this be solved by changing of coordinate system? Okay, mm, let us now. Hello, welcome back, students. So last time what we saw was r equal to r equal to twice of m was the problematic point. Okay, was the problematic point. This, so, but we have introduced a transformation in which we saw that this can be removed, and with the so-called tortoise coordinate. So can we have some more this suspicions, can we put it in a more stronger footing? So let us have some coordinate, okay, system change, so that we have that the suspicion that we are having, that this t equal to minus infinity and plus minus infinity are nothing but some blown up coordinates which are finite, but we are missing out on them. So let us, and that was first done by Eddington and Finkelstein, which is known as Eddington-Finkelstein coordinate. We can have two type of transformation. We can have defined u tilde, which is t plus r star. Okay, r star is defined above. Otherwise, or else we can have a v tilde, which is t minus r star. So you can check that in falling null geodesic are characterized by u tilde equal to constant, and outgoing null geodesic are characterized by v star equal to constant. You can check yourself. Okay, and this is the old space-time diagram in Schwarzschild coordinate of the Schwarzschild metric, and as I have shown that there are some suspicious thing going on here, and we are trying to avoid this type of singularity here. So what can be done? So we have next, what we have done is we have introduced this coordinate transformation. So for the Schwarzschild coordinate system, let us replace t with u tilde. Okay, if I do that, what happens? So let us now check the line element d square. It becomes minus 1 minus 2m by r du tilde. However, there are now this is the now it becomes diagonal. You can check with the we have learned this how uh, this metric coefficient changes with the changing coordinate system. Okay, that means g mu nu, let us say that g mu nu equal to gamma, not gamma, delta, yeah, g mu nu equal to delta mu alpha delta mu beta g alpha beta. Okay, by such transformation you can check the line element or the metric in your new coordinate system, and if you do it correctly, you will find that this is the metric, this is the final metric, which is given by say 1 minus 2m by minus of 1 minus 2m by r du tilde, these non-diagonal terms du dr and dr du, and however the other angular part remains the same. This is the two sphere part, okay, blown up by r square. You remember and you observe that each point in this diagram, each point is a two sphere, and how big is two sphere depends on what is the value of r. So very close to this r equal to 0, these are very small two sphere. However, as we increase or go to larger r, this two sphere grows. Okay, this you should remember that this each point is a two sphere with varying volume or varying radius. Okay, so you see that in this coordinate g mu nu and r equal to twice m is g 0 0, or the 0 0 component is 0, but that is okay, this can be 0, there is nothing harmful about it. Okay, it as long as it doesn't blows up, it's not a very serious issue. Now r equal to m is regular, which is locally. Okay, now in this coordinate system this is regular, so this is, there is no discontinuity, no jump, we can cross this r equal to 2m very smoothly if I go along this path. Okay, however, globally, this is the point of no return. This is also known as event horizon for the Schwarzschild metric. Okay, what does this point of no return means? We see that with u bar and r, we can cross the event horizon, which future directed path. Okay. Uh, However, if we have chosen instead of u, we have chosen to replace t by v tilde, we could have crossed the event horizon with past directed path. Okay, so we could have chosen a line like this or a line like that, and we can cross the event horizon r equal to twice m with some regular points. Okay, so yeah, this already I have told you. So let us see what happens. Okay, so how this space-time diagram in Erington-Finkelstein coordinate looks like. Let us plot it in v tilde and r. You can also plot it with u tilde and r. Okay, so v tilde r. This is a simple idea. This Einstein-Finkelstein coordinate. We choose such coordinate. Schwarzschild coordinate is replaced by some other coordinate system, and ingoing null geodesic. If I chose v tilde to be our this replacing if t is replaced by v tilde, we say the ingoing null geodesic have a slope of -1. However, the outgoing null geodesic are same. Okay, we have not done anything about it. Okay, so what this, and if I see the null cones are like this throughout. What we have done is that, however, we can now cross this r equal to twice m with this ingoing null geodesic without any harm regularly, right? The outgoing null geodesic still has a problem, which we have a suspicion that something is going on here. Okay, but we don't know. However, the incoming null geodesic, we can cross the event horizon without much difficulty. What we have done is that we have this. If I plot some outgoing null geodesic here, you will see that what we have done is that we have taken down the infinities which are acquiring, say, high up here. We are bringing that infinity down. We are pulling it downwards. And the infinities are not there. So we can then cross this event horizon with the ingoing null geodesic. So we have pulled the infinities down, and if once we have pulled infinities down, we can easily cross that. However, there is a problem still remains with the outgoing null geodesic. Okay. So what can we uh, conclude from this whole thing? First, we can conclude is that the Schwarzschild coordinate was not an ideal coordinate. It was not a good chart to describe the Einstein equation. So the Einstein equation describes a manifold. Okay. So, and the Schwarzschild coordinate was not an ideal coordinate to do that. We have chosen that, but this was our drawback. What it was only covering a part of the real world, and we are thinking that that is the whole world that is covering. However, that is not the case, because we have blown this t equal to plus minus infinity in both the directions, and we are thinking that it has covered the whole world. However, in the actual case, it was not. So this was the problem with Schwarzschild coordinate. This is not the ideal chart, and the chart has been it was a finite chart which covers a part of the Einstein equation, Einstein manifold, and uh, we have just inflated it. We have blown it upward and downward, and we have inflated it, and we have inflated, and we seemed like we have covered the whole Einstein manifold of the Einstein equation, which is covered by the Einstein equation. But it was not so. It was only covering a part of it. So the null geodesic were going to infinity at finite coordinate points. Okay, this was the basic problem with that. So we have changed the chart. So get rid, because we know this should not be the case. So we have changed the chart, and what we have changed the chart. What we get, this is something was happening beyond the boundary, like beyond the boundary, right here and upward here, either here or in the up direction. Something was happening there. Okay, and we have brought down the infinity, at least for the incoming null geodesic, to finite points, and we are able to cross the null event horizon with the going null geodesic without any problem. So can we improve upon this, right? We have done something very good with the ingoing, or either with the ingoing null geodesic or with the outgoing null geodesic, but we have not able to compress, means do this thing for the both the incoming and the outgoing null geodesic. However, things can be improved. Remember, we also have r equal to 0 to infinity. So can we change further coordinate transformation? We can do a further coordinate transformation and improve on this. What we want to look is that such that even the outgoing null geodesic have a slope of +1. Okay, can we do that? Means both the incoming and the outgoing. The incoming null geodesic has a slope of -1, and outgoing null geodesic has a slope of +1. Can we simultaneously do that? Yes, we can, and this was done in the Kruskal coordinate system. So let us look into what is Kruskal coordinate system. Okay, so instead of u and u bar, instead of changing t to u tilde or t to v tilde, let us change both t and r in coordinates u tilde and v tilde. Okay, then this metric can be written in terms of, this becomes 1/2 1 minus 2 gm by r d u tilde d v tilde plus d v tilde d u tilde plus this r square d omega square, which is the angular part. Okay, this remains the same. We have not done anything about this. This r can be also written in terms of this, with the recognition that half of u tilde minus v tilde is r plus 2m log of r minus 2m minus 1. So with this recognition we can write this, but there is no need. So we are mostly concerned about this, because these are already uh, uh, means regular coordinate system. There is no infinities compressed coordinate system. Okay, so so your next homework is to check with this transformation you get back this metric. Okay, you have to check that. So with this recognition, now what we have done is that this r equal to twice m, which was uh, happening in our coordinate system t and there was a coordinate singularity of the event horizon at r equal to twice m. What we have with this change of coordinate system, what we have made, that we have sent this to infinitely far away. Check it here. If I put r equal to twice m, this becomes infinity. So this becomes r plus infinity, and so this r equal to twice m have gone to infinity. So this r equal to twice m happens at either at u tilde equal to minus infinity or v tilde equal to plus infinity. Okay, so we have, instead of the infinity which was happening in a r equal to twice m, we have shifted it at plus minus infinity. However, uh, this is not also very good, because this was some point we want to look into. So how can pull them to finite values? We can pull them back to finite values. We can do that by now defining u prime as exponential u tilde by 4m, or v prime equal to e exponential minus of v tilde by 4m. And if you do that, you have to find this metric. Okay, and you have to find the metric and see that with this change you can you have some metric, and the infinities are not far away. But we are still not very good. I will tell you why we are not still happy with u prime and v prime coordinates in a minute. But later, before that, transformation. Okay, let us now define u to be half of u prime minus v prime, and v to be half of u prime plus v prime. If I do next this coordinate transformation, then my metric becomes ds square equal to 32 m cube by r exponential to the power minus r by twice m minus dv square plus du square plus r square d omega square. With the recognition, if I want to substitute r, that u square minus v square equal to r by twice m minus 1 exponential r by twice m. And this is known as this uv, the ds square in uv and theta phi is known as Kruskal coordinates, and the metric in Kruskal coordinates looks like this. Okay, so now let us check why we were not happy with u prime and v prime, and we chose to use u and v. See, this v is the time-like coordinates, and u, r, theta, phi are the space-like coordinate. Okay, you can easily check here with a constant factor, with a confound factor here. Okay, this is space-like. Our initial metric was again same. T was time-like, r, theta, phi was space-like. However, you remember u prime and v prime. You remember that they were not time-like or space-like coordinate. U prime and v prime were null coordinates. Null coordinates means, you can check that if I put this back, you will have they give 0. Okay, so u prime and v prime are null coordinates, whereas theta and phi were the space-like coordinates. So we were not happy with that. We wanted to always to go back to our the coordinate system, which was 1 time-like and 3 space-like. Okay, so we can preserve something with it. We will see what. Okay, so let us now look into some properties of this metric or this transformation, the whole thing we have done. Okay, so radial null lines look same as they do in the first place. That means they were having v equal to plus minus u equal to plus constant. Okay, some particular slope. Okay. And this is the slope of the sorry, this the radial null has already slope of plus minus 1 in this coordinate system. Okay, and v equal to plus minus u is the event horizon. The event horizon, which was infinitely away in say u prime and v prime, we have brought into towards a finite distance. Okay, the infinite level has been brought closer. The event horizon has been brought closer. That event horizon was something which we interested in, so we are not wanted to play with that and shift it to infinity. But we have done what we have removed the infinities there. The null coordinates and null lines are not infinite at v equal to plus minus u, and this infinity has been brought closer. Okay, and this r equal to constant hypersurface becomes u square minus v square equal to constant, and this is a very known equation. You can see that, right? This is the equation of a hyperbola in uv plane. Okay, so this is the first recognition that in this plane u square minus v square is a constant, is a hyperbola. Okay, and this is the r equal to constant hypersurface, and the surface of constant t, which is v by u equal to tan hyperbolic t by 4m. So what is this? This is a straight line through the origin with slope tan hyperbolic this. Okay, this is a straight line, so having a slope, this slope. Okay, so and as t tends to plus minus infinity, u equal to plus minus v. This u becomes either plus or minus v. So u and v becomes same. This becomes the slope. This line becomes of slope plus minus 1. Okay, so and the allowed region is u runs from minus infinity to plus infinity, and v square is less than u square plus 1. Okay, now if I draw this metric in Kruskal diagram, the entire space-time corresponding to the Schwarzschild metric, in Schwarzschild coordinate we only was getting some part of the Einstein solution of the Einstein equation. However, in Kruskal coordinates we get the whole space-time of the Schwarzschild metric. That can be we get the we get to see the whole manifold. So what this is the r equal to constant hypersurface. Okay, so this r equal to 0 is also constant hypersurface, and this is the line of r equal to 0, this and this. Okay, and this r equal to twice m is this line of this is a line of slope plus or minus 1. Okay, and this is r equal to twice m, t equal to plus equal to infinity, and this line is r equal to twice m, t equal to minus infinity. So this is seems like a hyperbola with these two lines running into it. Okay, so and always remember that each point is a point of a two sphere. Okay, so this point is a point of a two sphere, and it's blown out by it is how big is depends on the value of r. Okay, so some observation: the Schwarzschild diagram is only a part of the Kruskal diagram. See, this was the Schwarzschild diagram. This was the Schwarzschild diagram we are talking about. Okay, so we are only seeing a part of the Schwarzschild diagram, Schwarzschild metric in the Schwarzschild coordinates. Okay, but in Kruskal diagram we are getting all the whole manifold. Okay, so what are the different parts we can explore? Let us now check. So only this part was available to us. Okay, only this part was available to us in the Schwarzschild coordinates. However, we have got this part, this part, this part, and what are this part? Let us now check and what information that we get. Okay, so this is the same one. Okay, let us skip this. Okay, so let us now draw again the Kruskal coordinate, Schwarzschild metric in Kruskal coordinate. This is the whole manifold that we are looking into. So this is the region 1. Okay, where we started the Schwarzschild coordinate. Okay, and following the future directed null rays. So this is the future directed null rays. We start from somewhere from, let us say that we start from somewhere from here. We are following it. Okay, we are crossing this r equal to twice m twice m, and we are still going inward to hit till we hit r equal to 0. Okay, so following the future directed null rays, we reach region 2. So we reach this region. Okay, which is the black hole. Similarly, following the past directed null region, okay, we are approaching this region 3, and we are reaching something like this. Okay, so and we have a completely new region, which is the region 4, and we don't know, we have no hint of what this region was from the Schwarzschild coordinates, but we are getting this region, new region here. Okay, recognize this region 2 is the black hole, which we have been discussing, right? Now even light cannot come back. If light follows it, this is the time-like direction, so it has to follow until it hits r equal to 0, which is the black hole. Every future directed path in region 2 ends up to a singularity r equal to 0. Yes, so this any point will be always be hitting this r equal to 0 part. So it represents, we are utterly doomed, right? So it will always be converging to a black hole. So not only you, so you cannot even, if you are here, and if you have crossed this line, if you are here, so not only that you cannot come back here, you cannot even wander here. Okay, you just have to follow this time-like direction, and you just have to hit here. You cannot even wander here. Okay, you cannot even go through here. If you are here, you have to just follow this straight line and go and hit this r equal to 0 singularity. Okay, you cannot stop yourself from moving into the direction of the decrease. Simply this is the time-like direction. So region 3 is the time reversed of region 2. Okay, so part of the space-time from where things can escape to us, but we cannot never get there. Okay, this is also known as white hole. So see here, we cannot just go there. Everything can come, everything can emerge from here, and we can get there, but we cannot go in this direction. Okay, So this is the past directed line cones, part of the spectrum where things can escape to us, but we never get there. We will never be able to go there. Okay, region 4 cannot reach by region 1. Why can it cannot be reached by region 1? You can easily see that if I am a massless particle, I am light and a photon, what region can I go from here? I can only go here. I can always hit this region in region 2, and I can end in a black hole. Okay, I can also go, I can means something can come up here and come here back to region 1, come here can back to region 1, but we cannot, even light cannot go into this region, because light has a slope of plus minus 1, so it can only go in this direction or in this direction, but we cannot go into region 4. Okay, so there is no way to go to region 4. But however, this region 4 is an asymptotically flat region, which is a mirror image of region 1. Okay, so let us do some mind waving things in this region, let us say 4. Okay, let us take this cross sections like this. Okay, these are the cross sections. This is the, with, say, let us, this is t equal to 0, or some t equal to 0, this is some t equal to 1 or 2, this is something t equal to t1 prime, something like that. We have a taking cross section like this, but you should understand that these are not regular slices. Okay, even light only can go like this or like this. Okay, but however, let us assume that we can do this type of slices. Looks at the section that evolves like this. Okay, this sections, this may be unphysical or something physical is going on, we don't know still now. So such signal cannot be sent. Okay, if I want to send this type of signal, it cannot be done. But let us see what happens if I take this type of slope slices. And also remember that each point here is a two sphere, so of different sizes. Okay, so let us do is, let us restore one angular coordinate and draw the diagram of this slice. Okay, this is a point. Okay, let us draw this diagram at this point. Okay, and with restoring the angular coordinate, let us say phi. Okay, so what we get is that this is something region 1, this is something region 2. Okay, so this is some region 1, this is some region 2. Okay, region 4, sorry, this is one region 4, this is region 1, region 4, and they are connected by a neck-like region. Okay, this is called as Einstein-Rosen bridge. This is the t equal to 0. We have restored one angular coordinate that says a phi, and we see that this two asymptotically flat space-time has been connected by a neck-like region. Okay, which is known as, and this is the crossing point, this is the 0 point, this is the point which I'm talking here, and this point is a, if I resume one coordinate, right, this is r equal to twice m, okay, and t equal to 0, right, and if I do this for, say, phi equal to 2 pi, I will get this diagram, and this is known as the wormhole. Okay, this is the mind-blowing thing that we often used to think about. So region 1 and this, let us say that this is region 1 and this is region 2, or sorry, this is region 4. Okay, let us call now this region 2, and they are connected by through a wormhole. Two asymptotically flat region connected by a wormhole. However, no time-like or null-like observer can pass through this wormhole, because this is, as I said, that this, you cannot go like this. Even light can go like this. But if I have some space-like transmission, then we can pass through it. Or but this is all things which we should not talk about right now. So no time-like or null-like observer can pass through the wormhole. But if I can do that, then I can start from here and I can end in. I can start this from this with this asymptotically flat space-time, that is essentially flat world, which is us. And if I can do a this wormhole transmission and end up here, we will end up in some other space-time which is different from our world. Okay, this is the mind-blogging thing that people talk about, wormhole going through a wormhole or something like that. So next is, we can also have diagrams for, let us draw diagram for a star collapse. You see, this is the matter. Okay, it has some, say, it is star is collapsing, so it is going inside under its own gravity. So it starts with some finite value r equal to some finite which has some mass, and as it's collapsing it is going inward, and let us say that this is the Schwarzschild coordinate, okay, event horizon. So once it has crossed there, there is nothing to stop it. It has to hit r equal to 0, and then we will have a black hole. However, you can, this is in the Schwarzschild coordinate. You can draw even this in the Kruskal coordinate. This is the matter. This r equal to twice m gmi. Sorry about that. R equal to twice m. So matter starts here. It is collapsing. It is collapsing. It hits here, and this has to form a black hole. This r equal to 0 is the black hole in Kruskal diagram, and it hits here. So this is and also a diagram, a collapsing diagram in this TR space time and Kruskal diagram space time. Okay, so hello students, let us come back. So now is we will discuss, we have learned what are, how to get rid of some coordinate singularities, and we have seen that the Schwarzschild coordinates, the so-called Schwarzschild coordinate, was not a good coordinate to for the Einstein equation manifold. Okay, so we have gone into Kruskal coordinate, which has given us the whole new world of black holes, white holes, wormholes, and all of that. Okay, and we have seen much more world has been explored to us. Now let us now go to what is known as the Penrose diagram. What are Penrose diagram? So let us ask this. It would be very nice if the whole space-time can be drawn into a piece of paper. See, still the Kruskal diagram, we have not been able to draw the whole space-time in a piece of paper. Why? Because this was going here. Okay, there was some, we were not able to, this is going here, where it stopped, we don't know. Okay, however, it would have been very useful to us if the whole of the space-time can be drawn in a piece of paper. Okay, so this may be not a very, let us say it may not be the actual metric or the very physical one, but it can be an informative picture of the entire space-time in a finite portion of the of this paper. Okay, so this, is it possible? Yes, Penrose showed that it was possible, and it was possible for some space-time, not all. Some there are some space-time for which we cannot solve them. Okay, so let us now do for which for those space-time, look into for those space-time for which we can draw this Penrose diagram. But there are some constants which we should maintain during when we are trying to draw the Penrose diagram. What are the constants? The null geodesic runs at slope plus minus 1 in the diagram. Okay, so we know that even in our RT coordinate, the null geodesic was having the slope of plus minus 1. So constructing the future and past, because why we have done that? Because we were able to construct the future and the past null cones, and if they learn at plus minus 1, then we can looking at each and every point, we can say whether causality is preserved or not. Okay, so for preserving causality, we should have this condition. Okay, that the null geodesic should have this plus minus 1 in this diagram. So okay, so so how to draw this diagram? Let us look into the recipe book of drawing such diagram from any space-time metric. So the first point, let us start with the space-time metric given in some coordinate system. Okay, let us have any space-time metric we want to solve in any coordinate system. However, what we should always keep track, this is the very important, the most important thing that we should always keep track is the range of the coordinate. It changes. Let's keep the track of the coordinate range always. If I want changing from one transformation to another, we should always keep track of the ranges, how the ranges changes, because we want to bring infinite big diagram in a piece of paper. So we should keep track of the ranges. Second is find the coordinate such that the two previously non-compact. What does non-compact means? Non-compact means the coordinate which runs to infinity, either plus minus infinity or 0 to infinity. Anything which runs to infinity is called non-compact coordinates. So we should find a coordinate system that the previously non-compact coordinates are replaced Okay, let us say that let us replace by v and w, which are nothing but two null coordinates. Still they are non-compact, but now they are null coordinates. Okay, remember that this is the important point. So they are still non-compact, but we have changed the general this non-compact coordinates to now to non-compact null coordinates. Now the third step, the third recipe, we should compactify. We should compact this null coordinates into separately. This should be done separately. Okay, compactify means now they should not run to plus minus infinity or infinity, 0 to infinity, anything like that. You should run to some values, some finite values. How we can do that? Okay, one other very easy example is, let us say we change it from p from v to p and w to q. We can do that by tan inverse function. You see that tan inverse function. What is that? So v is runs from, this is the non-compact coordinate. Let's say v. This thing, same thing happens for w. Okay, so v can run from 0 to or minus infinity to plus infinity. Okay, however, if I do this transformation for every v, any v, the maximum value that p can have is always in the range between minus pi by 2 to plus pi by 2. So if I do this type of transformation, I can always compactify null non-compact coordinates to compact coordinates, and this is called the compactification of the coordinates. Okay, you can also have any other transformation that you like. I have introduced this as an example. Okay, so thus PQ takes the value in the range given by minus pi by 2 to pi by 2 and minus pi by 2 to pi by 2. Okay, so now we have compactified the coordinates. Next, let us see what we are going to do. Okay, 4. Define the temporal and spatial coordinates. See, if you do P and this type of compactification and null coordinates, you will mess up with the temporal and the spatial coordinate. So how to again go back to the temporal and spatial coordinate that we have started with. Usually you will see that there is one temporal coordinate and one spatial coordinate we start with. So we should also finally get back one temporal and one spatial coordinate. That can be done by, if I take t equal to p plus q, and this is the temporal and this is the spatial x is p minus q. Again, you should keep in mind, keep track of the ranges. Anywhere we are going there, keep track of the ranges. Okay, next, the fifth point of this recipe, what next to do? Okay, express the metric now in t and x and other in theta phi. So the whole metric can be expressed in terms of tx theta phi. Okay, this is the previously compact coordinates which we have not touched, and this are the two t and r coordinate, and we have again brought back in them in forms of t temporal and spatial part, but now in the compact form. So if such matrix takes the form, let us say that this is the metric element, omega squared to the power minus 2, omega to the power minus 2, which can be a function of tx, theta, phi, anything like that. This is the conformal part. Okay, and the metric inside looks like one temporal coordinate and three spatial coordinate, where this can be a function of the spatial temporal and the, which is multiplied by which has a coefficient. The angular part can be a coefficient of has a coefficient which is a function of t and x. Okay, if I can have this type of, if this metric can be written in terms of that, then we can obtain the non-physical diagram metric. This is the one. This is, now we are writing down the diagram metric because we want to draw the diagram and see the informative structure of what Penrose diagram can give us. So if I can, from this metric, I can, or if I can write the metric in coordinates t, x, theta, phi in this form, okay, and I can then obtain the non-physical diagram metric. This is the d square diagram, is only this part. Okay, I can do away with this. This is already compact. We did not know another because we always remember that each point in this, if I draw this diagram, each point in this is a 2 sphere which is multiplied by this factor. Okay, so if I do this, I can write the diagonal diagram metric of the form that which is of Minkowski space. However, you remember that Minkowski space, it was not finite, but here t and x are finite. Okay, so we can do this type of transformation, final transformation from some initial metric to this diagram metric. Okay, so this is a two-dimensional diagram always, and two-dimensional, this is the two dimension which are then usually the angular part is suppressed. So there are before we go and see an example of how to draw a diagram, there are special remarks which you should always keep in mind. First is in step 2, one chooses null coordinate because they preserve the cone structure. Yes, so once we have chosen the null coordinates, then the cones are fixed. We are not going to, the cones are not going to get squeezed. Okay, they are not going to get aligned in different way. Yeah, so this cone structure has been preserved, that means causality has been preserved. And the second remark that we should make is dropping the conformant factor omega to the power minus 2, which should not be equal to 0, does affect the shape of the time-like and space-like geodesic. Okay, so if I use in the diagram metric, the shape of the time-like and space-like geodesic should be affected, but not the null geodesic. Okay, the null geodesic, the shape of the null geodesic always remains same even in this diagram metric. Okay, the third homework is you prove that. Okay, prove this theorem or assumption that we have made. Now let us first draw the diagram, Penrose diagram for a Minkowski's metric. Okay, the Minkowski's metric is given by this metric coefficient. You see this theta and phi are the already compact form because it runs to finite values 0 to pi, and this runs from 0 to 2 pi. And however, this t and r are the non-compact. T is a much serious problem, it runs from minus infinity to plus infinity, whereas r runs from 0 to infinity. So we should be concerned about these two coordinates from the recipe that we have learned. Okay, now the second step is construct null coordinates. Although it may be non-compact, but you should now go back to construction of null coordinates. How we can do that? Just by this transformation, let us define t equal to t plus r, v equal to t plus r, and w equal to t minus r, suppressing the compact coordinates from the time for the time being. Okay, now this is so these are the, if this is t and this is r, now this is the v cone and this is the v coordinate and this is the w coordinate, and the portion which we are interested, because now let us keep track of the ranges. So r should be equal to half v minus w. Okay, from this two equation you can solve that r is v minus w, and this should be greater than this. Okay, this is the range, and if I plot this range in this diagram, you see that only this part of the portion is covered by the original metric. Okay, this part we are looking into. Okay, not this part, because here this means v minus w should be greater than 0. Okay, so next is if I want to write this metric, again you will find that you can write it doesn't I have mixed up this temporal and spatial coordinates. Okay, so these are two null coordinates. Okay, u and v. Okay, however they are even still now is not compact form. Now what we do is is now compactify. The third point is, remember, we have to compactify. So again, what the simple, we will change p to tan inverse v and q to tan inverse q. If I do that, so our you can always, as I've said, we can always use some other coordinate, other transformation, and choose any function you like which brings from infinity to some finite values. So in this range now, the track of the, if I keep the track of the range here, we can see that in this range p should be greater than q. Okay, this should be greater than this, and however p and q should belong to minus infinity, minus pi by 2 to pi by 2, and this is the covered portion of the diagram. Okay, but still we are not done. We have final transformation left, because see here, if your fourth homework is writing down this metric in this coordinate p and q. Okay, if you can do that, you will that we have mixed up this temporal and spatial part. So now again, to decouple it, what we make this final transformation, t equal to p plus q, and x equal to p minus q. Now if I do this transformation, now keep track of the ranges. So this becomes t plus x should be greater should lie between minus pi by 2 and pi by 2. P should lie between minus pi by 2 and p, and both p and q should lie between minus pi by 2 pi by 2. So half of t plus q should lie between this, and half of t minus x also should lie between minus pi by 2 to plus pi by 2, and this should be sorry, p should be greater than q gives us this relation. Okay, so I can also simplify this relation in terms of this. So t plus x lies between minus pi by and pi, and t minus x also lies between minus pi and pi, and x greater than 0. Okay, so this is from this equation I get this range. So the total metric in terms of t, x, theta, phi, you have to check that. Again, this is the fifth homework that you have to do, is check that this metric can be written in terms of 1/4 of tan inverse, sorry, tan square of half t plus x, tan square of half t minus x. This is not equal to 0, okay, which is the one of the condition. And inside part, see this, and inside part is multiplied by sine square x. This is the two sphere, which is multiplied by a factor in terms of the spatial part. Okay, however, this is in form of the Minkowski method. Okay, so we can drop we can write the diagram metric only with this. We can drop this and suppress this and write this diagram metric in terms of this. However, keep track of the ranges again. So this is the range remains fixed. Now let us plot this range in this in a piece of paper. So from, let us take this, okay, this part a1, this is, let us call this equation a, and this part of is 1, so t should be less than pi minus x. So what is pi minus x? So this part, okay, pi minus x is thus. So this is the whole region which we should consider, this whole region, t should be less than pi minus x. So this whole region is we are looking into. Okay, next from taking into this condition, t greater than minus pi minus x. So what is minus pi minus x? So this is minus pi minus x, so t should be greater than this. So this whole region, okay, this whole region. So we are now confined into a region between these two lines, straight lines. Okay, we are confined into these two straight lines, which is given by this condition A. Now, and what does condition B gives us? T should be less than, B means this, okay, this condition. So T should be less than pi plus x. What is pi plus x? So this is the pi plus x diagram line. So this is the pi plus x, so it should be less than. So this should be here. So we are now confined within. So the first we are confined. We have, with the first condition we are confined into all of this space. Now we are subtracting this space. We are only concerned about the space which is there. Okay. The second condition, t greater than minus pi plus x, is this line. Okay. So we are only left with this space in this rhombus. Okay. So we are into this rhombus. And the third condition, x greater than 0, right? This is capital X. X greater than 0 is, we are only, so this is the x less than 0, so we are only concerned with this triangular part. So this is the triangular part which is our area of concern. Okay, and remember that light rays travels in straight lines with slope plus minus 1. So this is light rays which goes like this, or either like this, like this. Okay, so this is the Penrose diagram which you are looking into. Let us now draw it separately. So we have identified the Penrose diagram, and let us now draw it separately. So this is the Penrose diagram. Okay, we have identified, remember in this diagram the two dimensions are suppressed, okay, theta and phi. So we have identified some points here. This is called I plus point, this is the I0 point, and this is the I minus point. So what is I0 point? I0 point is space like infinity. This r equal to infinity or something like that. This has been compressed to I0. Okay. I plus. is the future time like infinity, okay, which was t equal to plus infinity. So I has been confined to I plus. Okay, I minus is past time like infinity. I minus t equal to minus infinity has come here. Okay, now this is chi plus. So this is future null infinity. Okay, line means null race should always end here. Okay, I plus. So this is the future null infinity. This whole line is the future null infinity. Okay, and chi minus, sky minus is the past line null infinity. Okay, so null race all should begin here with sky minus and always end at sky plus. Okay, so and you should space like this is the space like infinity. So space like geodesic should start here, go like this, somewhere like this, and always come back here. Okay, so and as I told you, null geodesic starts at I minus and end at I plus. Starts here, null geodesic, and end here. It can be in here, like this. They should always learn with so plus minus 1. Time like geodesic should start as I minus and end at I plus. So time like geodesic should go like this. Should go like this. Okay. So now what we can do is we can reinstate one phi parameter because we have each point is a two sphere, remember? So let us reinstate the phi parameter. So what can we do? We rotate this point. Okay. If I rotate this point, what we give is this. We get this type of uh, cone, double cone type structure. Okay, it's very difficult to think of, but it's like uh, in both rhombus which is rotating. Okay, and this is the I0 line. The point here, point becomes aligned with the circular line. Okay, and you remember that the space like geodesic should always start here, go somewhere here, and always come back somewhere here, and always come here. Light should start here, like that, go somewhere here, and either can stop here or go and stop here. You can start here, go here, or here. Okay, this is the null geodesic, but always they have to be plus minus 1, and time like geodesic can run from this like this. Okay, you can figure out, you can discuss and think about and more. So this is the Penrose diagram of Minkowski's metric. Okay, so net we can also draw the space-time diagram for Schwarzschild metric. That is the Maximilian extent. That is the Kruskal coordinates. Okay, so if you this is a homework. Try plotting this. Okay, Penrose diagram for Schwarzschild metric. If you do it correctly, we'll see that you will get this type of diagram. Okay, so this is the whole black hole, right? This is the black hole part. It's not a point. I plus is not a point. It is this curvy line. This is the white hole with curvy line. Okay, and this is the I minus point. This is the I plus point. This is I. We have two I plus and two I minus point, which is connecting the region 1 and say region 4. This is region 2 and 3 are the black holes and the white holes. Okay, and these are the null geodesics, the straight lines. Okay, coming from here, it's always they will start from here and always end up like this tri minus. Sorry, yeah, this can always start from here and always end in a black hole. There is no other way to go. Okay, and these are the time like geodesics. Okay, they have to start at I minus and end at I plus. Time like geodesic can happen here. Okay, so this is the Penrose diagram of a Schwarzschild metric. Your homework is finding out this, all the transformation laws and all those things. Do it; it's fun. It's really. We can also have a Penrose diagram for vibrational collapse. So again, this is I minus, this is I plus, this is the black hole. So this is the matter part, which is not given by Schwarzschild metric. We will know what metric this does this given by. We will learn. Okay, so this is a time like this. However, this particle are massive particles, so this should be a time like part, time like geodesic. It start at I minus and it will end at I plus. I plus is the whole. This whole line is I plus. Okay, so this is the Schwarzschild radius. Okay, something like this. So once it crosses the Schwarzschild, this is a collapsing star accretion collapse of star, so it ends in a black hole. Okay, you can draw many other metric in Penrose diagram. So it's very informative. We have got all this uh, mm, points where null geodesic starts, and there is nothing running away to infinity. This only in a finite portion of paper. Okay, so this is the beautiful diagram that Penrose are. Although this is a non-physical diagram, but it's a very informative structure. You can learn many things about space-time metric, which was not covered by Schwarzschild metric from these diagrams.